Hey everyone, Nitesh this side. Hope you are doing well. So let's start with the question. So the question is shortest path visiting all nodes, and it's a hard level question. So like I try many times and I saw the discuss section and also the hint of the question. And after that I was able to solve the question. So let's see how what's the question and how we will solve this question. Okay, so you have an undirected connected graph of n nodes, basically labeled from 0 to n minus 1. So it's an undirected graph. Basically, you can go in any direction. And you are given an array graph where graph I is a list of node connected with node I by an edge. So it's basically representing adjacency list. What you have to return the length of the shortest path that visits every node. You may start and stop at any node. You may revisit node multiple times and you may reuse edges. So basically you have given an undirected graph and you have to traverse all the vertices. Like you can traverse from 0, 1, 2, 3 in any direction, and you have to give the minimum path which you will follow. So let's see with an example. Okay, so we have given this graph. So let's see this graph. Okay, so let's say we will start from here. Okay, so let's say we will start from this node. Okay, so we will start from here. Okay, now we have three options. Like we can go in this direction, we can go in this direction, and in this direction. Let's say we will go in one. Okay, so we can choose this. Similarly, now we reach here. Okay, now we have only one option to return back because we have to traverse 2 and 3 also. So 2 and 3 is not connecting to 1, so we will return back to 0. So we will come here, so we will at here. Okay, now we have other option in 0, 2 and 3. So let's say we choose 2. Okay, now for 2 we'll again return back 2 because 2 is not connecting to any other vertices, so we will return back, so it will be 0. Now let's say we'll reach 3. Okay, so if you count the path, so it's basically 1, 2, 3, 4, 5. Okay, so this take 5 path. Okay, let's see how we can see other approaches also. Okay, let's see other path also. Let's say we will start from here. Okay, so we will start from here. So one, we can only have one option, so we can go in 0. With 0, let's say we'll go to 2. Okay, so with 2 we can return back to again 0. Okay, and with 0 we can reach to 3. So as you can see, we take 4 edges, 1, 2, 3, 4. So this is the 4, basically the path. Okay, so you have several paths, but you have to give the minimum path, and for this case this is the minimum path. Okay, so let's see how we can approach this. Basically, if you got the intuition, like we need to find the minimum path. Okay, so we need to find minimum path, and minimum path we can only find out in graph by BFS. Okay, so we got to know, like we need to find the minimum path, and the best approach we can use is BFS. Okay, so let's see how we can approach this question with BFS. Okay, so we need to find the minimum distance, and we know like with the graph we can use BFS. Okay, so let's see, like if you know about the BFS, we will take only one node at a time and basically traverse its all neighbors. Okay, and what we are doing is basically we will store a visited array. Okay, so every time whenever we take this, we will mark it as visited. Similarly, we will go to its neighbor and mark it visited. But in this question, it is mentioned like you can visit the same vertex again. Okay, so if you go with the normal BFS and you just like you will go to this child. Okay, so you reach at this point. Now you can't roll back because this is already visited. Okay, so we need something like which can help us to roll back to this position. Okay, so with the normal BFS we are facing this problem. Okay, so let's say, so this is the first problem that we are facing, like with the visited array we can't reach to our solution, so not able to reach solution. Okay, now there will be, like you can say, remove the visited array. Okay, so let's say you remove the visited array and you go from 0 to 1. Okay, now with 1 you have option to roll back it again 0. Okay, now with 0 you don't have a visited array. You again have three option, 1, 2, 3. Okay. So what you can go, you can again go in the one vertex. Then similarly, so it will cause a cycle to you basically. So the second problem is if we remove your visited array, then it will cause a cycle. Okay, so these are the two problems that we are facing with normal BFS. Okay, so what we need is uh basically a BFS with which can store the visited and also stores like also create like which will store like this will not create cycle, not create. Okay, so these two things which are important for us for to do the BFS. Okay, so let's see how we can modify our normal BFS. Okay, so we got to know like we need something which will store visited path and also no cycle is created, because with normal BFS we are lacking with these 2 points. Okay, so let's say for the BFS what we are using, like for BFS we use generally queue. Okay, so if you take this node, you can't really show like this will give you the minimum path. So you have to take all the nodes and traverse all the visited path and also check whether cycle is created or not. So what we will do, like instead of inserting one node at a time, we will insert every node. Okay, so this will solve our problem more easily. Okay, and we'll see how we can get some basically visited array which can do these two steps. Okay, so what we will do, we will take a queue and we will insert all the vertices in this 0, 1, 2. So it's basically like a simultaneous BFS. Okay, simultaneous, because with the 0 we can go with some path, but with 1 also we can again have the same path which 0 also travels. Okay, so what we will do after this, like 0 will pop out and 0 will add its children. So it's like 0, 1, similarly 0, like I pop out this, it will become 0, 2, 0, 3. Okay. Similarly, 1 will pop out and it will add its children. So 1, 0, and similarly 2 and 3 also. So 2, 0 and 3, 0. Okay. So why we are going with simultaneous BFS? Because with 0, if you take this vertex and you go any path, that can also be go with the same or different vertices also. So that's why we take a simultaneous BFS which can basically use the same path again, so that same path will not traverse again and again in different vertices. Okay, so we got it, like we need a simultaneous BFS, but we need something which can give this, like this path is already visited and the cycle is also not created. So let's see how we can get this, or how can we resolve this. Okay, so let's see how we can get which can store visited and also cycle is not created. So let's take this graph 0, 1 and 2. Okay, so now what we can we can use a mask. Okay, I will explain you how mask will help us. Okay, so what we can see, if I have to store like 0 is visited, how can I store is I can store 0 like this. If I give them in a binary form, so it will be 0, 0, or let's say 1 second. So this will be 0, 0, and taking it as 1, 2, 3, 4. So this will be 1, 1, 2, 3, 4. Okay. So 0 will represent it like this. Similarly, if I have to represent 1, so it will be like 0, 0, 1, 0. Okay. So this is like 0, 1, 2, 3 are just like a 2 to the power. So it's 2 to the power 0, 2 to the power 1, 2 to the power 2. I just write down the power in bottom. Similarly, if I have to write 2, so it will be 0, 1, 0, 0. So it should be like this. Okay. 3, 2, 1, 0. Okay. Now what we need, like if let's say I have traversed a path, let's say my path is 0, 1, 2, and I need to give them a mask. So what will be the mask for this? So mask for this, if I traverse like 3, 2, 1, 0, it will be like 1, 1, 1, 0. Okay. So, and you can also say like your path is 0 to something. So you will represent it like this: 0, 1, 0, 1. Okay. So masking will help us to check whether the same path is visited or not. Okay. So let's see with an example like how we can approach this question. So we got to know for the visited we need to do some masking. Okay, so what will the maximum mask value if I need to represent it? So let's say I have visited like this 0, like the path for this is 0, 1, and I again come to 0 and I again come to 2. So if I need to mask them, so it will be like 3, 2, 1, 0. So 1, 1, 1. Okay. So as you can see, if you know like this is n equal to 3 for this case, and if I do 2 to the power 3 equal to 8. So if I represent it in a, like this is a binary format, so this will be 7. So the maximum value I can go till this 8 minus 1. Okay. So what I will do, I will create a 2D array. Okay. So 2D array is basically which will represent the mask and also the current vertex that you are visited. Okay. So let's create a 2D graph. Okay, so we need a 2D array. So for that, our row will be like this will be our n, and our column will be 2 to the power n. So this will represent the maximum mask that you can take. So for this case, n equal to 3, and this will be 2 to the power 3 equal to 8. So let's create a DP array basically. Okay, so what we will do, and we will initialize all the value of this DP with -1. Okay. Okay, so we have created our visited or a DP array, and -1 will be represent that this vertex or this mask is not visited. So this is the mask and this is your vertex. Okay, so for the BFS we need a queue. Okay, so let's take a queue, and this queue will be of a type of array, so it will take two parameters. Okay, so this will take two parameters. First is your current vertex and the mask for that. Okay, so what we will do, let's create a queue. Okay, so this is our queue. Let's write down the adjacency list for this. So for 0 it will be like 1 comma 2, for 1 it will be 0, for 2 it will be 0. Okay, so what we will do, for the first time we will insert all the vertex into the queue. Okay, so and queue is type of a vertex and a mask. Okay, so what we will do, we will take this vertex, so we will take this 0th vertex and insert it into our queue. So we will take the 0th one and calculate the mask for 0. Okay, so with the starting, the initial mask will be 0. We will pass the 0 and it will be your current, and side by side you need to pass the current vertex also. Okay, let's see how we will calculate the mask. So mask is just like you will do mask or, and you will do left shift or your current vertex. Okay, so this will be your mask, like your initial value, and this will be your vertex. Okay, so for this case what we will do, mask will calculate, so this will pass as 0, and you have to do OR with one left shift of your current vertex. Okay, so if you do the left shift of 1, it will remain as 1, and 0s or 1 will give you 1. Okay, so what we will do, we will insert this into our queue, but before inserting we need to check whether it is already visited or not. So how can we check? So we will check the current vertex is 0 and the mask is for this is 1. So we will check at 0, 1 coordinate. So we will check whether 0, 1 is it not equal to -1. So right now it is -1, that means it's not visited. So we will mark it as 0 and we will insert this into our queue. Okay. Now we'll calculate the mask for 1. So we'll take 1, we'll calculate the mask. So our initial value for mask is 0 and your vertex is 1. Okay. So you will call this function and what it will do? It will do 0, 𝗁, 1 left shift of vertex. Okay. So if you do the 1 left shift of 1, it will give you, like, you can represent it in a binary. So this will be 0, 0, 1. This is equal to 1. And when you do the left shift of this for one time, it will become 0, 0, 1, 0. And it will give you 2. Okay. So this is now 0, 𝗁, 2. And if you do the OR with 0, it will give you 2. Okay. So for the 1, we again need to check whether 1, 2 is visited or not. So 1, 2, it's not visited, it's -1. So we'll make it as 0 and we will insert in the queue also. Okay. Similarly, we do for this vertex also. So this will become 2 and you call this function mask 0, 2. Okay. So this is now become 0 or 1 left shift of 2. Okay. So if we do the left shift for twice, so it will become 0, 1, 0, 0. And if you represent it in a integer decimal format, so it will give you 4. Okay. So now this will be, your vertex is 2 and your mask is 4. So you will check in the array 2, 4, is it visited? No, it is not visited. So we will mark it as visited by making it 0 and you will insert this 2, 4. Okay. So this will be our first step. We need to insert all the vertices into our queue. And then after that, we will pop out one element and do its neighboring child. Okay. Okay. So you have done with the initial step, like you inserted all your vertex into this DP array and start with the 0. Like you take all the vertex every time, like simultaneously make it as 0. So it will start from 0. Now we need to check the other vertices also. Okay. So we will pop out this. So we will first pop out this and we will pop out this 0, 1. Okay. So for the 0th vertex, okay, we have two options. Either we can go 1 or either we can go 2. Okay, so let's say we will start from 1. So what we will do, we will go to 1 and calculate the mask for this. Okay, so for this, the mask will be the older mask. So this will be our older mask. Okay, like in the earlier you start from 0th mask, but now you have the mask already. So you will pass this 1 and you will pass your current vertex and you will pass this to this function. So set mask. Okay. So what it will do, it will take your mask as 1 current mask and you will do 1 left shift of 1. Okay. So 1 left shift of 1 will give you 2. Okay. So this will be 1 0 2 and 1 0 2 equal to 3. Okay. So now you got the new variable as 1 comma 3 and you will check whether 1 3 is visited or not. So you got the new part, you check 1 comma 3, you see it is -1. That means it's also not visited. So what you will do, you will make it not 0, but you will do, you will check your previous distance, like previous DP value. So for this case 0 1 0 1 you have 0. So what you will do, you will take this value and do the +1. Okay. So if you are at here and reaching this point, you will take this edge. So taking this path will cause you 1. So that's why we increase by 1. So this will be 1 and you will insert it here 1 3. Okay. Now you have second vertex also from here. So you will take this 2. Okay. So you will take this 2. Now for the 2, what you will do, again you will pass your older mask. So mask is this and you will give your current variable, current vertex. So 1 comma 2. So this will be, if you can see, your mask is 1. So you just write down mask and 1 left shift of 2. So 1 left shift of 2 will be 1 or 4 and it will be 5. Okay. So this time it is 2 comma 5. So with 2 comma 5, you again check whether it is visited or not. So 2 comma 5 is not visited. You will mark it as, like, you will take this value and do the +1. So this will become 1 and you will insert this here also. Okay, so we have done the 0 comma 1 children, 0th vertex children. Now we will pop out the next element. Okay, so we will pop out this 1 2 1 comma 2. Okay, so with the 1 2 we can see with 1 we have an option to go to the 0th vertex again. So from here we can go to 0. Okay, so we can go in 0. So 0, and with 0 we will calculate the mask for this. So we will pass the older mask. Older mask is 2, and your current vertex is 0. Okay, so you can see 2 or 1 left shift of 0. So 2 left shift of 0, it will give you 3. So now your variable is 0 comma 3, this path. So you will check whether 0 comma 3 is visited. So it is not visited. What you will do, you will check for 1 2 and increment it by 1. So this will become 1, and you will insert this here. Okay, now we'll pop out this element because for 1 we have traversed all the children. Similarly for 2, let's write down 2 comma 4. Okay, so with 2 what we can see is we can go to this child, so 0. Okay, so we will mark it's 0, and we'll take the older mask as 4, and 1 basically pass this vertex. So this will be 4, 1 left shift of 0. Okay, so 1 left shift of 0, it will give you 5. Okay, so now it will be 0 comma 5. So you will check whether 0 comma 5 is visited. No, it is not visited. So you will mark it as visited, and you will increase this value by 1. Okay, so, and you will insert it. Now we have done for this children. Now let's take out this. Okay, so let's move forward. Okay, oh, there is one mistake we have done when we pop out this element 1 2. Okay, so 1 2, for 1 we have 0 children. Okay, so this will be 0, and for 0 if you calculate the mask will be take the older mask, and you will pass the current vertex. So this will be 2 comma 0, and 2 1 left shift of 0. So this will give you 3, and you mark 0 comma 3 as basically as +1. So this will be 1, and we have inserted 1 2 instead of, so we need to insert 0 3. Okay, so this is the mistake we have done. So it's 0 3. Okay, now let's move forward. So let's pop out this 1 3 element. Okay, so we have pop out this 1 3. Okay, so 1 3 we can see we can take this 0 vertex, so 0, and for the 0 we'll calculate the mask. So this will be, we'll take older mask 3, and we'll pass the current vertex. So this will be 3 left mask of 1 left shift of 0. So if you do the 1 or 3, it will give you 3. So 0 comma 3. Okay, so you will check for 0 comma 3, and 0 comma 3 it's already visited, so you will not do anything, you will just continue. Okay, now you will take, for the 1 we have covered all the children. Now you will take 2 comma 5. Okay, so you will take this 2 comma 5. You, for 2 again we have 0 children, so we will take this, and we'll calculate the mask for this. So 5 comma 0 will pass 5 or 1 left shift of 0. So this will give you 5. You will check for 0 comma 5. You will check 0 comma 5, it's already visited, so you will do continue. So this is also pop out from this. Now let's take this 0 3. Okay, you take this 0 3. Now with 0 you again have two option, 1 or 2. Okay, so let's say we take 2 first. Okay, so we take this 2, and for the 2 if you calculate the mask, it will be, you take the older mask, it will be 3, and you will pass the current vertex as 2. So it will be 3 or 1 left shift of 2. It will give you 4, 1 left shift of 2, and if you do the OR of 3 or 4, like this will be 0 1 1, and this will be 1 0 0. So OR of this 1 1 1, it will give you 7. Okay, so so you will check whether this 0 7 is it visited. Sorry, it will be 2 comma 7. So 2 comma 7 is not visited, so I will mark it as +1, and it is coming from 1, so you will increase it value by 1, so it will become 2. And whenever you reach in the last column, that means you got your mask, because this is the maximum value till we can reach. Like if I just write down, it will be like 1, because we reach from 1 to 0 and 0 to 2. So 1 0 2. If I represent it in mask, it will be 1 1 1, and this is the maximum value that you can reach. So whenever you reach at the end of the column value, you will just return this value, and this is your final output. Okay, So I hope this will be clear to you. Let's write a code for this. Okay, so have already written the code. Actually, the video is going long. So what we need is, so we need a queue. Okay, so for our BFS, we need a queue. Okay, and we take a n as a graph length. We take our row, we take the column. So column we calculate as 2 to the power n. Okay, now we take a visited or a distance array. So distance array we created and we initialize its all value by -1. Okay, so this is our initial step. This is our initial step. So what we are doing is basically create the mask of your current vertex. So we'll create a mask. We get the mask, and after that, what we will do, we will insert into our queue. So how we are inserting? So this will be my vertex, and this is my mask. So I will insert it, and I will mark the initial distance by 0. Okay. So this is my initial step. Now we need to do some work. Okay. So what we are doing is we will take out one element at a time. Okay. So we will take out one element. We take so element 0 will represent our current vertex and element 1 will represent your current mask. Okay, so we will check whether if we reach our mask equal to column -1, which will means we'll reach to our last end column. So that means we got our final answer and we just return the minimum distance from there. Okay, but let's say we will not reach. So what we will do, we will iterate its children or its neighbors. Okay, so what we are doing is we were iterating over a current vertex. So we'll do a enhance loop over this. We take this new vertex as child and we calculate the mask for this new children. So we calculate the mask. In this we pass our older mask which we get from here. Okay, and we pass the current vertex. So we'll pass this current vertex and we got the mask. And let's say if it is not equal to -1, that means it is already visited. Okay, so this is already visited, so we don't need to do anything, we just continue. But if it is not visited, what we need to do, we need to increase the value by +1 and insert into the queue. Okay, so this will be the final code for this. And if you want to see the code for set mask, so set mask is basically, okay, so this is the set mask function that I already explained you. So we will take a current mask and we will do OR with the left shift of 1 with the current vertex. Okay, so let's, and the time complexity for this is basically, okay, so time complexity is basically what you are doing is you are creating the mask for each vertex. So maximum mask you can achieve, like you can, like if you can see, we can go in any direction. We have this, we have this, we have this. Similarly for this, you can go in this direction for this. So maximum mask you can get it for this 2 to the power n, and you will do for all the vertex. Okay, so this will be the time complexity, and space will also with this that we create a distance array. Okay, and I forgot to run, so let's run the code. Okay, so this is accepted. Let's submit it. And this is also accepted. So hope you like my video. Thank you for watching this.